stop scrolling for 10 seconds, because this one fact is going to mess with your intuition. The universe we can see is not the whole universe. It's a bubble around us, about 46.5 billion light-years in radius, limited by the speed of light and the universe's 13.8 billion-year history. Beyond that horizon, there could be more space, more galaxies, and depending on which laws of physics you think are fundamental, possibly other universes that are not just far away, but fundamentally disconnected. That's the real idea behind parallel universes, and it's way less sci-fi than people assume, and also way more controversial than most videos admit. Here's the pattern interrupt. When people argue about the multiverse, they often act like it's one theory. It's not. It's a family of ideas that come from different parts of physics, and they don't all rise or fall together. Some are almost a boring consequence of well-tested math. Others are on the edge of philosophy, where even Nobel-level physicists disagree about whether it's science at all. Let's start with the least dramatic but most important version. If space is infinite, or just vastly larger than what we can observe, then what we call our universe is just the observable patch. That's not a separate universe with different laws. It's the same universe, just beyond our horizon. Is space infinite? We don't know. Measurements of the universe's geometry from the cosmic microwave background and galaxy surveys show space is extremely close to flat. So close that, if it's curved, the curvature is tiny. Flatness is consistent with an infinite universe, but it doesn't prove it. Still, the key point is already humbling. Everything that exists is not what your eyes, telescopes, or even the James Webb Space Telescope can access. Now, the second idea is where parallel universes gets its reputation: cosmic inflation. Inflation is a period of extremely rapid expansion in the early universe proposed to explain why the universe looks so uniform in all directions and why it's so close to geometrically flat. And this is not a fringe idea. Inflation also predicts a specific pattern of tiny temperature variations in the cosmic microwave background, variations first measured in detail by missions like COBE, then WMAP, and then Planck. Planck's results match a key inflationary prediction. The primordial fluctuations are close to scale invariant, with a measured spectral index around 0.965, not exactly 1. That's a big win for inflation as a framework. But here comes the controversy. Some versions of inflation naturally become eternal inflation. The basic reason is quantum randomness. In these models, while inflation ends in one region, creating a hot Big Bang, like universe such as ours, other regions keep inflating. Picture it like this. Inflation doesn't end everywhere at once. It ends in patches. Each patch becomes a bubble universe, and the overall space continues expanding so fast that bubbles can be forever separated. That's a kind of multiverse. Do we have direct evidence of other bubbles? No, and that matters. Scientists have looked for possible signatures, like weird circular patterns or anomalies in the cosmic microwave background that might hint at a collision between bubble universes. So far, nothing is conclusive. Also, inflation predicts primordial gravitational waves that could leave a specific B-mode polarization imprint in the cosmic microwave background. Experiments like Bicep/Keck and Planck have not detected that primordial signal yet, but they have placed strong upper limits on it, often reported as an upper bound on the tensor-to-scalar ratio, for example, are constrained to be below a few percent in combined analyses. That doesn't kill inflation, but it does rule out some inflation models and pushes the remaining ones into narrower territory. Here's a retention twist. Even if inflation is correct, eternal inflation might still be wrong. Inflation is a framework, not one single mechanism, and different inflation models behave differently. So when you hear inflation proves the multiverse, that's not accurate. What's accurate is, inflation is strongly supported as an explanation for early universe conditions, and some leading inflation models imply a multiverse. Now the third big parallel universe idea isn't about space at all. It's about quantum mechanics. You've probably heard the line, "In another universe, you chose differently." That's the pop version. The actual idea is the many-worlds interpretation proposed by Hugh Everett in the 1950s. In quantum mechanics, the math that evolves the wave function is smooth and deterministic. The weird part is measurement, why we observe one outcome. Many-worlds says, the wave function never collapses. Instead, the universe's quantum state evolves into branches, where each outcome exists in a different branch. Here's the part that makes scientists argue at conferences. Many-worlds does not change the equations of quantum mechanics. It's an interpretation, meaning, it's a story about what the equations mean. And as of now, it doesn't produce a clear, unique experimental prediction that distinguishes it from other interpretations like Copenhagen. That's why some physicists like it. It avoids adding extra collapse rules. And that's why some physicists hate it. It feels like multiplying realities without new testable power. The debate isn't, is it cool? The debate is it necessary? And does it clarify probability? Pattern interrupt number 2. You don't have to believe in many worlds to believe quantum mechanics is real. Quantum mechanics is among the most precisely tested frameworks in all of science. The parallel universe part is about what you think reality is doing behind the math. Now for the fourth multiverse idea, string theory's landscape. String theory is an attempt at a consistent quantum theory that includes gravity. One surprising outcome is that the theory seems to allow an enormous number of possible vacua, different low-energy configurations that could correspond to different particle physics and different constants of nature. People sometimes quote numbers like 10 to the power of 500 possible solutions. The exact counting depends on assumptions, and the details are technical, but the core point is, the space of possibilities may be huge. This is where the controversy hits maximum volume. If there are many possible sets of physical constants, and inflation can populate different regions with different vacua, then our universe could be one region where the constants happen to allow complex chemistry and observers. That leads to anthropic reasoning. We observe conditions compatible with our existence because if they weren't, we wouldn't be here to observe them. Some scientists see this as a powerful selection effect. Others see it as surrender, because if anything can happen somewhere, what exactly are we predicting? To be fair, there's at least one famous case where anthropic-style reasoning got attention, the cosmological constant problem. The observed value of dark energy is tiny but non-zero, discovered in 1998 via supernova measurements. Long before precision measurements, some arguments suggested that if the cosmological constant were much larger, galaxies wouldn't form, so observers wouldn't exist. That doesn't prove a multiverse, but it's part of why the idea refuses to die. So where does that leave us, right now, with updated, honest science? 1. We do not have observational proof of other universes. None. If anyone tells you we do, they're selling you certainty, not physics. 2. We do have strong evidence that our observable universe is only a patch of a larger reality, simply because of horizons and cosmic expansion. That's not a multiverse by itself, but it's the doorway that makes the question scientifically sharp. 3. Inflation is supported by multiple lines of cosmological data, but eternal inflation and bubble universes are plausible extensions, not confirmed facts. Researchers are actively narrowing inflation models with better measurements of the cosmic microwave background, large-scale structure, and gravitational wave constraints. 4. Many worlds is a serious interpretation held by serious physicists, but it's still an interpretation. It's not settled, and it's not experimentally singled out. 5. String landscape multiverse ideas are mathematically motivated but remain speculative. And the biggest criticism is testability. Science advances by risking being wrong. And here's the final pattern interrupt. Even if the multiverse exists, it doesn't automatically make anything possible. Physics still constrains what kinds of universes can exist, what structures can form, and what observations can occur. Many universes is not the same as no rules. In fact, The multiverse debate is really a debate about what the rules are and how we can know them. If you want more science content that separates what we know, what we suspect, and what we're still arguing about, follow this account so you don't miss the next one. And now I want to hand the controversy to you. Do you think parallel universes belong in physics as a testable scientific idea, or do you think they cross the line into philosophy, and why?